Hello, the purpose of this video is to continue talking about properties of matrix operations. The first properties we're going to be looking at deal with addition and scalar multiplication. I have a list here of properties and all of them are very sensible and easy to check. If you remember, addition of matrices is done component-wise. Here's a quick example. I'll take the matrices with 1, 2, 3, 4, and 5, 6, 7, 8 as entries and add them together. Of course, addition itself is commutative, so it doesn't matter whether I added A plus B or B plus A. All of the other properties on this list are also easy to check. Here's a quick example that deals with scalar multiplication. Let me now take the matrix 1, 1, 0, 1 and scalar multiply times 4 times 3, or 12. So I could think of this as being 4 times the matrix that's filled with 3, 3, 0, 3 by first scalar multiplying by 3. And that also gives me the matrix with 12, 12, 0, 12 as the entries. This is demonstrating property number 3, by the way. So all of these properties are quite sensible, and I encourage you to check them all on your own time. Another set of properties that we're just going to kind of speed through are those that deal with the zero matrix. So we're going to use the notation 0 and then in the subscript mn to denote a matrix whose entries are all zeros. This is called the zero matrix. So clearly, if you take any matrix A and you add it to the zero matrix of the correct dimension, you're going to get the same matrix A back because you're just adding 0 to all of the entries. Likewise, if you take A plus minus A, where minus A is the matrix that you get by scalar multiplying by -1, it should produce for you the zero matrix. And finally, if a scalar multiple times your matrix A gives you the zero matrix, then either the scalar was 0 or the matrix that you started out with consisted only of zeros. So using these properties, we can work through an example that's going to demonstrate some of them. So let's solve the following problem. We're going to be considering a matrix equation, much like we would consider a basic algebraic equation. So we're going to solve for x. We're going to solve for x when 3x plus a is equal to b, where a and b are 2 by 2 matrices given right here. So let's go ahead and solve for x and use some of these properties of matrix operations. So as we want to solve for x, we would write 3x is equal, 3x plus a is equal to b, and that means that x, or 3x, is equal to b minus a, and 1/3 times 3x, which is equal to x, is 1/3 as a scalar times the matrix b minus a. And now I can go and solve for what this matrix x ought to be. So in particular, let me work out what 1/3 times b minus a is. Okay, so 1/3 is going to be scalar multiplied times the matrix 1, 2, 4, minus 5, minus the matrix 2, 1, minus 3, 0. So this gives me, inside the parentheses, another 2 by 2 matrix with entries 1 minus 2. So that's a -1, 1 minus 1, so that's 0. 4, minus 3, 7, and a -5. And then I would scalar multiply through by this 1/3, giving me some fractional entries, -1/3, 0, 7/3, and -5/3. And this is the matrix X that solves that equation. Another set of properties that I kind of want to fly through and then leave you to check on your own are the properties that deal with matrix multiplication. So implicit in this list of rules that I've written down is that A and B and C have the correct dimensions so that you're allowed to multiply them together. Remember from before that if we're going to be multiplying two matrices A and B together, then we need that if A is m by n, then B better be n by something. And what we need is that this n and this n match in order for matrix multiplication to be well defined. Okay, so the first thing on the rule is that A times B times C is A times B times C. And so you would say this is associative. And then we also have a collection of distributive type rules in 2 and 3, and another rule for scalar multiplication. So I encourage you to make up small examples to check these. Let's look at one quick example. Of course, this is not a proof. This is just an example to demonstrate one of these rules. Let's take a closer look at rule number 4 that involves scalar multiplication. So in this example, I'm going to use a scalar 7. And I'm going to take 7, and I am going to first scalar multiply 7 times the matrix 1, 0, 0, 2. When I do that, that means all of the entries get multiplied by 7. And then I'm going to matrix multiply by the matrix that I would be calling B here. So this here is 7A being multiplied times the matrix B. And then I follow my rules for matrix multiplication. So when I do that, I would take row dot product with column vector, row from A dotted with column of B. And that actually gives me an entry of 0 in the first spot. And then I take the first row of A dotted with the second column of B, and that will give me this entry of 7. The second row dotted with the first column, giving me a 14. And the second row dotted with the second column, giving me the entry 0. So this is now 7A matrix multiplied to B. Now, rule 4 here tells me that's not the only way to carry this out. I could have also taken the matrix A and multiplied it to the matrix CB. And if we write that down for this example, we would see something like this. Here we would have the matrix A times CB, where this is A, and here's the scalar C being multiplied times the matrix B in parentheses. The next example is a kind of important one to demonstrate that you cannot cancel matrices in the way that you do when you're solving ordinary algebraic expressions. So let me explain what I mean by that. In this next example, we're going to take 3 2x2 matrices. So we could multiply A times B or B times C or A times C. All of these different products are well defined. But look at the following calculation. Let's notice here that if I take A times C, that's these two matrices multiplied together. And matrix multiplication will produce -2, 4, -1, 2. Make sure that you understand why I get these entries for A times C. And if I take B times C and multiply these together, then I get the following: -2, 4, -1, 2. Ah, I have the same thing here. So this calculation tells me that AC is equal to BC. I just worked it out and confirmed that that was true. But A is not equal to B. These are distinct matrices with different entries. So I cannot cancel C from this equation. So this is essentially what I mean by this example demonstrates why you cannot cancel. Or at least you cannot always cancel matrices in this way. So what exactly is going on here? If this were an ordinary algebraic expression, meaning I'm taking A and B and C now, lowercase, to be real numbers, and let's say C is not 0, then I would be able to cancel. For ordinary numbers, if I have that AC is equal to BC, it does mean that A is equal to B. But why can I write something like this? That's because C has what's called a multiplicative inverse. So if C is a non-zero real number, well, so is 1 over C. And when you cancel C from an equation like this, what you're really doing is multiplying times 1 over C. A times C times 1 over C is equal to B times C times 1 over C. And then these C's and 1 over C's cancel with each other in the sense that when you multiply them together, you get a 1, which leaves for me that A is equal to B. That's how numbers work. But that's not how all matrices work, because not every matrix has a matrix inverse. So that's what's really going on in this example. We're going to talk a lot more about matrix inverses in the near future. But the takeaway from this example is that here, this matrix C is what's called not invertible. C inverse, the multiplicative inverse, does not exist. This is an important concept, and we'll be spending a lot more time with matrix inverses in the future. Next up, we're going to be going over just a little bit of terminology. So we're going to be discussing identity matrices. They've probably already come up. But when I talk about the identity matrix, what I mean is a square matrix, which has ones down the diagonal and zeros everywhere else. So the 2 by 2 identity matrix looks like 1, 0, 0, 1. The 3 by 3 identity matrix has 1, 0, 0 in the first row. And it's convenient sometimes to leave out the zeros because it's a lot of zeros to write down for writing things in real time. So this is kind of the abbreviated way of writing down an identity matrix, IN, or you can jot down some ones down the diagonal. So they're always going to be n by n, meaning they're square matrices. It's a really easy check to see that if you have an m by n matrix, then if you multiply A times the n by n identity matrix or multiply the m by m identity matrix times A, you get back A. So it is the identity in the sense that it is the multiplicative identity matrix. A times I is equal to A. Another piece of terminology that we toss around a lot in linear algebra are symmetric and skew symmetric matrices. So a symmetric matrix is going to be symmetric about its diagonal. I have a quick little example of each of these. So you have some numbers down the diagonal. In this case, it's 1, 3, and 1. And the symmetry of the matrix is about this diagonal. So let me pick a green color here. So I see a 2 and a 2. This is the axis of symmetry. And so these entries are all going to match up in this way. Let me now erase that so you can see the entries. The more concise way of writing this type of symmetry is to say that entry Aij is exactly equal to entry Aji. So when I look in spot 1, 2, it agrees with spot 2, 1. When I look in spot 3, 2, it agrees with spot 2, 3. Skew symmetric means that the symmetry has a negative sign in it. So for a skew symmetric matrix, what we expect to see is that entry Aij is equal to the negative of entry Aji. So again, we have the same axis of symmetry going down the diagonal, but when we compare entry 2, 1, it's the negative of entry 1, 2. And when we look at entry, say, 3, 1, it's the negative of entry 1, 3.